Today, we shall be looking at chemical equilibrium. Chemical equilibrium can be defined as the state where there is no observable change in the properties of a system with respect to time. This simply means that both the forward and the backward reaction in a reversible reaction is equal. So there is no observable change. Equilibrium system may be static, which means may be stationary, or dynamic, which means in constant motion. So a dynamic equilibrium is the one that is in constant motion. There is movement. Equilibrium in reversible reaction. Now, a reversible reaction is denoted by the symbol which is displayed in parentheses. Now, if we have A plus B producing C and D, then the reversible symbol will be in between the reactant and the product. When we see that reversible symbol, which involves both forward and backward arrow, then that equation is a reversible reaction. And the reversible reaction is said to be in dynamic equilibrium when both the forward and the backward reactions are occurring at the same rates, thereby no net change in the concentration of the reactant or product. Moving to factors affecting chemical equilibrium. Chatellier's principle or law of mobile equilibrium is used to predict the effect of a change on equilibrium of a chemical reaction when the system is subjected to a stress from certain factor. So these scientists actually predicted that when a chemical reaction is subjected to a stress, then this chemical reaction will decide to neutralize those factors that caused the change or the stress, so that the equilibrium will be reversed, or the equilibrium will be restored. Now, Chatelier principle states that if a chemical system is in equilibrium and one of the factors involved in the equilibrium is altered, the equilibrium will shift so as to neutralize the effect of the change. So this is how it stated the principle. Now, from the principle, the main factors affecting equilibrium positions are: number one is effect of temperature. Number two is effect of concentration, change of either the reactant or the product. The third one is the effect of pressure on change of equilibrium. Now, effect of pressure is only for gases. Let's take it one after the other. Number one, effect of temperature change. When we are looking at effect of temperature change, we have to look into two types of reaction so that the explanation will be meaningful. The first one is effect on endothermic reactions. As we all know, this reaction is the one that needs heat energy. It absorbs energy from the environment. So, having noted that, according to Chatellier's principle, 1. Increase in temperature causes equilibrium to shift to the right, favoring the forward reaction, and equilibrium constant K increases. Then decrease in temperature causes vice versa, just like the opposite of the first one. Now let me re-explain again. For endothermic reaction, it absorbs heat from the environment. So, meaning that a reaction which is endothermic can never take place, or will be reluctant to take place by itself without heat. So, naturally, it needs heat energy. Therefore, when you supply heat energy to it, you are doing it a favor, because that is what it needs from the onset. So an endothermic reaction, anytime you increase the temperature of heat of that endothermic reaction, the equilibrium position shifts to the right, meaning you are favoring that endothermic reaction. Now let's go to the second one, the B part, effect on exothermic reaction. Now, this is a reaction that does not need heat energy. So in the same manner, like I've already explained, and in opposite to the former one I explained, exothermic do not need heat. So which means it can occur spontaneously. It can happen on its own. So if you supply it to it, you are not favoring it because it does not need it. Now let's move forward. According to Le Chatelier's principle, 1. Increase in temperature cause equilibrium to shift to the left, favoring the backward reaction, and equilibrium constant K decreases. Can you see? Because it does not need heat. It can actually happen on its own, spontaneously, or probably we can say that it has sufficient energy within itself, its content, to happen. So supplying more energy, more heat energy, you are disfavoring the forward reaction. You are just favoring the backward reaction. Going to the second factor, number 2, effect of concentration change. According to Le Chatelier's principle, increase in concentration of reactant or decrease in concentration of product causes equilibrium to shift to the right, favoring the forward reaction. This is simple. When you increase the amount of the reactant, then the equilibrium will shift to the right. Which means if you have your raw materials and you want to produce more of your goods or products, then you need to increase the raw material. And when you increase the raw materials, then you are favoring the production of your product. That means we have more product to get. And in like manner, if you decrease the concentration or the amount of the product, you are also saying that more of the reactant should be converted to the product. So you are also favoring the forward reaction. Then secondly, decrease in concentration of reactant or increase in concentration of product causes equilibrium to shift to the left, favoring the backward reaction. It's just opposite to the previous one explained. Now to the third factor, effect of pressure change on gases. Now pressure affects gaseous state always. Let's look at the equation below. Nitrogen gas plus hydrogen gas to produce 2 molecules of ammonia, NH3. From the reactant angle, when we add 1 molecule of nitrogen plus 3 molecules of hydrogen, it gives us 4 molecules. So the reactant side, we have 4 molecules or simply 4 volumes. Then from the product side, we have 2 molecules or simply 2 volumes. We could link that to Avogadro's, law or Avogadro's law. Note that when volume is increased, it means the pressure is decreased, according to Boyle's law. The Boyle's law states that the pressure of a given mass of gas is inversely proportional to the volume, provided the temperature remains constant. So, in that case, the inverse proportionality then means when the pressure is higher, the volume is lower. Or when the volume is higher, the pressure is lower. So, having 4 moles or 4 volume at the reactant means the pressure is small compared to the product side, which have 2. Let's move further. From the equation above, A, the forward reaction, which is 4 to 2 volumes, shows a decrease in pressure, which means the forward reaction is not favored. So if you look at that point very well, 4 to 2 volumes as a whole, it means that the pressure is decreased simply because 4 at the reactant is greater than 2 at the product. 4 volumes at the reactant side is greater than 2 volumes at the product side. It means that the pressure that should have compressed the reactant to force them to produce more of the product is too small. So the pressure is lower. Then the B, the backward reaction, which shows 2 going to 4. 2 going to 4 volumes shows an increase in pressure, which means the backward reaction is favored. So we have to look at from 2 to 4 now. It means that if the product side, which is having 2 volumes, is smaller than the reactor side, which is having 4 volumes, it means there are more pressure that forced the product to go to the reactant side. Backward reaction is favored. Now, according to Le Chatelier's principle, increase in pressure causes equilibrium to shift to the right, favoring the forward reaction. can we see that when we now increase the pressure of this particular reaction, which is 1 mole of nitrogen plus 3 moles of hydrogen to produce 2 moles of ammonia, when we increase the pressure, the equilibrium will shift to the right, because from the reactant side we have 4 volumes and the product side we have 2 volumes. So we are forcing the 4 volumes to compress or to be converted to give us more of the product. So mathematically, what we are looking at is that if initially we have 4 to 2, we are then saying by the time you increase the pressure, we are going to have 3 to 3. Then if the pressure continues to increase, we are going to have 2 to 4, 1 to 5, and finally 0 to 6. Then on the other side, decrease in pressure causes equilibrium to shift to the left, favoring the backward reaction. Note, a catalyst does not affect equilibrium position because it does not change equilibrium constant K. So it cannot shift equilibrium to the right or left. However, a catalyst affects the rate of reaction by, number 1, lowering activation energy, speeding up both forward and reverse reaction equally, helping the system reach equilibrium faster. So this is what a catalyst does. It doesn't affect the position of equilibrium. So the only thing it does is to affect the rates of chemical reaction. So how does it affect them? By the 3 things being listed here: lowering activation energy, speeding up both forward and reverse reaction, and helping equilibrium reach its ends faster. The final equilibrium composition is the same, it just gets there more quickly. Equilibrium constant is a measure of the ratio of the equilibrium concentration of the products of a reaction to the equilibrium concentration of the reactant, with each concentration raised to the power corresponding to the coefficient in the balanced equation of the reaction. Now that definition explains the fact that the equilibrium constant is equal to the product over the reactant. So we can see from that formula, in the general form reaction below, small letter A, capital letter A, plus small letter B, capital letter B, to produce small letter C, capital letter C, plus small letter D, capital letter D. Those small letters refers to as the mole or the coefficient. So the equilibrium constant K is equals to C raised to power C multiplied by D raised to power D all over A raised to power A multiplied by B raised to power B, where the bracket sign means equilibrium concentration, Kc means equilibrium constant used when equilibrium concentrations are expressed in molarity, and the unit is mole per dm cube or capital M. Kp means equilibrium constant calculated from partial pressures used when equilibrium concentrations are expressed in atmospheric pressure. Now let's look at equilibrium concentrations. In a state of chemical equilibrium, the concentrations of the equilibrium mixtures can be deduced as follows. Number 1, reaction that involve only one reactant. Only one reactant. So if a reaction involves a reactant, this is how the concentrations will be calculated. Now, A to B. Initial concentration. The concentration or the mole or the amount, which is small letter A, is written under the reactant A. Then at the initial point, B has 0 concentration because B has not yet been produced or formed. Then in row 2, reacting concentration, we have X, and under B we also have X. It means that as the time goes on, B has started forming, or B, at least some amount of B has started being produced. So at that particular time, the amount being formed from A is X, and the amount being disappeared from A is also X. Then the row 3, equilibrium concentration. Now, which means when the reaction is at equilibrium, the concentration will now be A minus X under A, and the concentration will be X under B. Then number 2, reaction that involves 2 reactants. which means A plus B, to give C plus D. So in this case, the initial concentration will be A under capital letter A, B under reactant B, then 0 under product C, and 0 under product D at the initial level. Then when the reaction is going on, the reacting concentration will be XX all through, because the amount that disappears from A or B is the same amount that appears under C and D. So equilibrium concentration at equilibrium state, under A will be A minus X, under B will be B minus X, and under C and D will be X and X. 3. Reaction in which the initial concentration and of the product is given. There could be that in a particular reactions, at the beginning, you already know the concentration has been, of the product has been given. Probably you have some product already on ground, so you just want to produce more and add to it. It means you already have some amount, at hand. So any amount you are producing will just be added to the one on ground. So at initial concentration, we have A under reactant A, B under reactant B, and C under reactant C, because we have the initial concentration of C. At reacting concentration level, we also have XXX. Like I said the other time, amount disappearing from A and B is the same thing as amount appearing under C or other product. Equilibrium concentration will not be under A minus X, under B minus X, and under C plus X. C plus X. I repeat, C plus X. We could look at the definition of terms there. Initial concentration means the original concentration at time 0. Reacting concentration, which is X, is the same thing as concentration of reactants that disappeared. And then equilibrium concentration is the same thing as final or left or remaining concentration at time T. Let us see some worked examples. The following results were obtained during the analysis of the chemical reaction. CO2 plus H2 given H2O plus CO. Now the concentration of CO2 is 0.7 molar. Concentration of H2 is 0.32 molar. Concentration of H2O is 0.30 molar, and concentration of CO is 0.55 molar. Calculate the equilibrium concentration constant of the reaction. In this case, our Kc will be equal to the concentration, the product of the concentration of the product over the product of the concentration of the reactant raised to the power of their coefficient. So water and CO are the reactants. So like we have seen there, H2O raised to the power of 1 multiplied by CO raised to the power of 1 all over CO2 raised to the power of 1 multiplied by H2 raised to the power of 1. So the product will be up, the reactant will be down. You see? Then we do a substitution of the various concentration, then it produces 0.688. Number 2 question. Consider the following equation. Hydrogen gas plus iodine gas to give us 2 molecules of hydrogen iodide. If the partial pressure of 45 degrees C of H2 is 0.065 atm, I2 is 0.45 atm, and HI is 0.245 atm, calculate A, the concentration constant Kp for the forward reaction, B, the equilibrium constant Kp for the backward reaction. Now let's look at the solution. For A, for the forward reaction, Kp, now we are using Kp here because the unit is talking about pressure and all atm partial pressure, so we are using Kp. So Kp is equals to the Hi raised to power 2, that is the hydrogen iodide raised to power its coefficient, over hydrogen gas to the power of its coefficient multiplied by iodine gas to the power of its coefficient, which after substitution gives us 2.05. Then B, for the backward reaction. Now the backward reaction is just the inverse of the forward reaction. That's all, which means 1 over 2.05 given 0.488. Now let's look at example 3. A. When 8.28 gram of the ethanol were heated with 60 gram of ethanoic acid, 49.74 gram of the acid remained at equilibrium. Calculate the value of Kc. B. What mass of ethyl ethanoate should be present in the equilibrium mixture formed above from 13.8 gram of ethanol and 12 gram of ethanoic acid under the same conditions? Now, from the two questions of number 3, I mean A and B, we could infer that B part says under the same condition, which means the Kc from question 1 will be the same thing as the Kc in question 2. So firstly, let's look for Kc in question 1. Now, solution. We need to get the balanced equation, which is very necessary for any calculation in chemistry. Make sure you write out your balanced equation. So our balanced equation is C2H2 C2H5OH plus CH3COOH to produce CH3COO C2H5 plus H2O. Now that equation is already balanced. Now we go back to the question A. We are going to change the mass given there to number of mole, because the number of mole will be the concentration we will be working with. So it will represent our concentration, because that is what we are going to be using in this calculation. So the initial number of mole of ethanol will be 8.28 divided by 46. That is the mass of ethanol divided by the molar mass of ethanol, and it gives us 0.18 moles of ethanol. So we've converted that mass of ethanol to number of mole, which is our initial concentration. Then we go to ethanoic acid. We also convert ethanoic acid to mole. So 60 divided by 60 to give 1 mole. Then the third mass given in the question is the remaining amount of ethanoic acid. So we also convert it to number of mole. That's 49.74 divided by 60 to give us 0.829 moles. Now we bring down the equation down. We bring down the equation back again in order to determine the equilibrium concentrations. So the equilibrium concentrations of the two reactants and the two products. Now we rearrange our equation as we are seeing. Initial concentration of ethanol is 0.18 written under ethanol. That of ethanoic acid 1 written under ethanol. Now we do not have initial concentration for ethyl ethanoate and water, so we are going to write 0, 0 under the two of them, because products are not yet formed at that time. Now to the second row, where we have reacting concentrations, RC. How do we get 0.171? We have to refer back to the formula of number 2 previously written, whereby reacting concentration will be X. That means X means the amount disappearing from the reactant, which is equal to the amount appearing under the product. So from that memory, we know that all the concentration at that level should be represented by XX. Then how do we now know that in this case our X is 0.171? Now let's go to row 3, equilibrium concentration. From the question, it has been given that ethanoic acid that remain at equilibrium is 0.829 moles. Do not forget that we've converted the mass that remain to number of moles. So the 0.829 moles that remains under ethanoic acid, we subtract it from 1. So we now know the X for ethanoic acid. The reacting concentration for ethanoic acid will now be 0.171. And the moment we get the reacting concentration of one of the reacting species, then it's the same thing for all. The moment you know one of the reacting concentrations of the reacting species, then it will be equal to the reacting concentration of the rest. since it's the same thing, they are all x, 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 x. So because 1 minus 0.829 is equals to 0.171, then all other reactant species, the ethanol, the ethyl ethanoate, and the water automatically become 0.171. Then in the row 3, going back to the row 3, then we will now subtract under ethanol, C2H5OH, you will subtract 0.171 from 0.18. Then it will give us 0.009. Then under ethyl ethanoate from the product side, since there is no initial concentration, we have 0 there. Whatever you do at the product side is addition. 0 plus 0.171, the equilibrium concentration will give us 0.171. The same thing with the water. 0 plus 0.171 will still give us 0.171, all at equilibrium concentration level. Then we move to the formula, the Kc. Don't forget the product raised to power their coefficient over the reactant raised to power their coefficient. Then when you substitute what you got at the level of equilibrium concentrations, substitute it into the formula, it will give us 3.92. Now going to the B part. The B part says we should calculate the mass of ethyl ethanoate at equilibrium. Now in the B part, they give us different masses. They didn't give us the mass of any of them that are left at equilibrium. So it means that we are looking for X. Initial number of mole of ethanol for the question for the B part now will be 13.8 over 46, which is now 0.3 moles. Then the second one is number of mole of ethanoic acid, 12 over 60, to give us 0.2 moles. So we've converted the two moles, the two masses of ethanol and ethanoic acid to number of mole. So this number of mole is what we are going to impute into the equation. Now coming back to the equation so that we can determine the equilibrium concentrations. Like we did initially, the first row is our initial concentration row. We place all the concentration there, 0.3 under ethanol, 0.2 under ethanoic acid, 0 under ethyl ethanoate, and 0 under water. Then the second row, reacting concentration, we put XXXX there. Why? Because they did not give us the reacting concentration and they did not tell us the amount remained or left or the final. So we don't know. We are not privy to that. So the third row, which is the equilibrium concentration, now what we do to the reactant side is to minus so that we know the amount remained or left. So 0.3 minus X will be written under ethanol. 0.2 minus X will be written under ethanoic acid. 0 plus X, don't forget, after the arrow is addition. So 0 plus X is X under ethyl ethanoate. 0 plus X is X under water. Then we go back to our equation formula again. Kc is equals to the product raised to the power of their coefficient over the reactant raised to the power of their coefficient. You substitute your values, all the value you got under equilibrium concentration, put in there. That of ethyl ethanoate is X raised to power 1. That of multiplied by that of water, X raised to power 1, all over that of ethanol, 0.3 minus X raised to power 1, multiplied by 0.2 minus X raised to power 1. So you can see that substituting these values, we turn the denominator to a quadratic equation when you multiply the both values. Then we are going to get 3.92. The 3.92 is our Kc gotten from question 3a, because it was stated under the same condition. So we are using the same condition for B. 3.92 is equals to X squared over 0.06 minus 0.5X plus X squared. Then you will do what is called cross multiplication in order for us to get a linear equation. And after all, the equation becomes 2.92 X squared minus 1.96 X plus 0.235. Now, the value of the X in the quadratic equation can be calculated using the general formula, which is X is equals to minus B plus or minus square root B squared minus 4AC all over 2A. We all know that general formula for quadratic equation, which will be used to solve the question. Then after using the formula, our X value, if you use the formula carefully, after substitution, the X value will be 0.514 or 0.158. Don't forget, for this quadratic equation, you will get two values. Now, look at the two answers. 0.514 is higher than the two initial concentration of ethanol and ethanoic acid. Ethanol is 0.3, ethanoic acid is 0.2. Now the first answer here is 0.514 is higher than the two of them, so it is impossible for 0.5 to disappear from an amount that is smaller than it, which means our answer will be 0.158 because it is smaller than the initial concentrations. So since the number of mole that reacted, X, cannot be more than the initial concentration of both the ethanol and the acid, therefore X is 0.15 moles. So the number of mole of ethyl ethanoate is 0.158. Now that we have gotten the number of mole of ethyl ethanoate, which is X, right, then we convert that to mass to get our final answer. So since our mass, number of moles is equal to mass over molar mass, then mass is equal to number of mole times molar mass. Then the mole we got, 0.158 multiplied by 88, which is the molar mass of ethyl ethanoate, will give us 13.9 grams. So this will give us the final answer. Thank you for listening.